I want to tell you something about a student I watched during a classroom visit a few years back. 5th grade, multiplication of fractions, and this student could execute. They could execute the procedure perfectly. Multiply the numerators, multiply the denominators, simplify, if needed, every problem on the page correct. The teacher was pleased, the student looked confident, and everything about it looked fine on the surface. Then the teacher asked one question. She said, "Does multiplying always make a number bigger?" And the student said yes, without even hesitating. Absolutely yes. Multiplying makes things bigger. That's what multiplication does. The teacher pointed to the problem the student had just solved. 1/2 times 1/3 equals 1/6. And she said, "Is 1/6 bigger than 1/2? And the student looked at the paper, looked at the teacher, looked at the paper again, and something changed in their face that I've never forgotten. What that student was experiencing in that moment wasn't really confusion about fractions. It was the specific disorienting feeling of someone whose foundation just moved underneath them. This procedure had been working. The answers had been correct. None of it had been built on anything solid enough to hold the weight of one follow-up question. That student didn't have a fraction problem. They had a number sense problem, probably one that had been building and accumulating underneath a surface of correct answers for years. Welcome to Show Me the Math Receipts. I'm Asali Smith, founder of Number Navigators, and this is episode 11. Today, we're going to go back, all the way back to the beginning, before the algorithm, before the procedure, before any of it. We're talking about number sense, what it is, how it develops, and what happens across a child's entire mathematical education when we skip it and move straight to steps. So let's get into it. Over to you, Josh.
It's time for Math Joke of the Day. What do you get when you cross math with a bug? Arithmetics. But ching.
All right, thanks, Josh. So let's go. Before we get into the research, I want to name something because number sense is one of those terms that gets used all the time and defined almost never. Number sense isn't knowing your facts. It isn't being able to count quickly, recite a multiplication table, or execute a procedure accurately. And those things are valuable in their own right, just not the same thing. Number sense is the intuitive feel for how numbers work. It's understanding that numbers have size and relationship and context, and that 99 is close to 100, and that closeness actually matters. That multiplying by a fraction less than 1 makes something smaller instead of bigger. 7 groups of 8 and 8 groups of 7 land on the same total through completely different arrangements. And an answer of -47 for a question about how many students are in a math classroom should stop you cold because it doesn't make sense. And knowing it doesn't make sense is basically the whole thing. Number sense is what lets a student look at a problem and get a feeling about it before they even solve it. A sense of the neighborhood the answer lives in. A gut check that catches errors before they turn into wrong answers turned in for a grade. And this is what makes the conversation urgent. Number sense doesn't come from procedures or from algorithms or timed tests or pages of practice problems executed correctly. It comes from experience, concrete, varied, richly structured experience with quantities and relationships and patterns starting early and kept up over time. Every year we skip that foundational work to move faster towards the steps. We're building on ground that isn't ready to hold what we're about to put on top of it. Now, there's a strong body of research on number sense and how it connects to mathematical success. And I want to walk you through the parts that really matter the most. Herbert Ginsberg at Columbia spent decades studying the mathematical development of young children, and his work kept showing that children arrive at school with a lot more mathematical intuition than we usually give them credit for. They come in with informal knowledge of quantity, of comparison, of grouping. So number sense, it isn't something that we pour into kids. It's something that we either cultivate or we interrupt. The classrooms that build strong mathematical thinkers versus the ones that don't often come down to what gets protected and developed in those early years, before the formal mathematics even starts, more than what gets added on top later. Jordan, Kaplan, Remeneni, and Lukuniak ran a landmark longitudinal study that followed kids from kindergarten through third grade. And they found that a child's number sense in kindergarten predicted their math achievement in third grade more reliably than general cognitive ability, working memory, or a reading skill did. That's worth pausing on for a second. More reliably than how generally capable a child was. More reliably than memory or reading. Number sense, the intuitive feel for how numbers work, built before anybody ever opens a textbook, turned out to matter more than nearly anything else we usually measure. Then there's the work of Stanislas Dehaene, cognitive neuroscientist whose book, The Number Sense, looks at how the human brain processes quantity. His research found that humans are born with a rudimentary sense of number, an ability to tell small quantities apart that show up even in infants. What that early capacity turns into over time depends almost entirely on the experiences a child has with numbers in those early years. The brain shows up ready to build number sense. Whether instruction actually meets it there is a different question. So what happens when it doesn't meet the child there? We get exactly what I described in the opening. A student who can execute a procedure correctly and can't answer a single follow-up question about what it actually means. Who multiplies fractions accurately and still believes that multiplication always makes things bigger. Somebody who's learned to perform mathematics without ever developing a feel for it. And that student is going to hit a wall eventually. Maybe in middle school when proportional reasoning shows up. Maybe later in algebra, once negative numbers stop being rules to memorize and start requiring real understanding. Or on some standardized test where the problem's framed in a way the procedure alone just can't handle. The wall is coming. Skipping number sense is what builds that wall. Now let me make this concrete, because number sense instruction doesn't look like a special program or a separate curriculum. It looks like intentional daily choices about what we ask students to do with numbers before we ever ask them to compute. Take what skipping number sense actually looks like in a classroom. A teacher introduces multiplication with the standard algorithm. Students practice it, and they practice it, they master it, and the unit assessment shows strong results, so the teacher moves on. Then 4 months later, when fractions show up, those same students who executed the algorithm perfectly have no conceptual framework for understanding that multiplying can actually make something smaller. Nobody ever asked them to think about what multiplication actually means. The procedure was always the destination, and the understanding was just assumed to come along for the ride. Now, take what building number sense actually looks like before the algorithm for multiplication ever shows up. Students spend time building equal groups with manipulatives, drawing arrays, exploring what happens when you change the size of a group. They make estimates. Is 7 times 8 going to be closer to 40 or closer to 80? And how do you know before you even calculate? And then along the way, they're talking through their reasoning. They're comparing strategies. They're noticing patterns. By the time the algorithm finally arrives, it's landing on soil that's already been prepared to receive it. The procedure connects to something the student has already understood in their body and in their language and in their reasoning. And so it holds. That second classroom takes longer getting started, but it gets to the algorithm more reliably in the end because the foundation's there to build on. So let me say something about what this looks like across grade levels too, because number sense work isn't only an early childhood conversation, even though that's where it starts. In middle school, number sense shows up as proportional reasoning, the ability to feel the relationship between quantities before you even set up a ratio. A student who has it can look at a proportion and sense whether it's reasonable. A student who doesn't can cross-multiply correctly and land on an answer that's wildly off without any internal alarm going off at all. In high school, it shows up as an algebraic intuition, the ability to look at an equation and have some feel for what neighborhood the solution should live in. Kids who have that intuition catch their own errors. Kids who don't just execute the procedure and accept whatever comes out on the other end. Even answers that make no mathematical sense at all. The foundation built in early childhood echoes through every grade level that follows, which is really just to say the time spent building, it's never wasted. It might be the single most leveraged instructional investment that a teacher can make. If you're a classroom teacher, here's one reframe that I think will change how you plan each lesson. Before you introduce a new mathematical concept, ask yourself what you want students to be able to feel about it before they calculate it. What's the intuition you're actually trying to build? What should the neighborhood of the solution look like in a child's mind before the procedure ever shows up? If you can't answer that, the concept probably isn't ready to be taught procedurally yet. So go back and build the feel first. The calculation, it will follow from there. If you're a math coach, number sense is one of the most revealing lenses that you can bring into a math classroom visit. It's less about whether the students are getting correct answers and more about whether they can tell you something true about the answer before they even calculate it. Whether they can estimate, catch an unreasonable result, explain why an answer makes sense rather than just that it happens to be correct. Those are the real indicators of number sense in action. And when they're missing from a classroom, you've found the gap worth addressing before anything else. If you're an instructional leader, let me ask you something that might sting a little. Look at your curriculum from kindergarten through 5th grade. How much time is set aside for building number sense before algorithms get introduced? How much of your early math instruction is built around exploration, estimation, and sense-making versus practice and procedure? If that balance is tilted heavily towards procedure, the outcomes that you're seeing in middle school aren't really a mystery. They're the predictable result of a foundation that got skipped. And the fix probably isn't more intervention in middle school, it's more foundation, building back in the early grades. And if you're a pre-service teacher, this is the thing I want you to carry into your first classroom. Every student you teach walks in with mathematical intuition. Every single one. Your job in the early years isn't to replace that intuition with procedures. It's to build on it, connecting the formal mathematics to what kids already sense about quantities and relationships, and protecting the number sense that they came in with. The fastest way to destroy it is teaching procedures before that intuition has had a chance to become real understanding. So here are your Wednesday morning receipts. 3 things this week. First, start every lesson with an estimate. Before any computation happens, before students even pick up a pencil, ask them to estimate. What's a reasonable answer? What's an unreasonable answer? How do you know? What does the neighborhood of this answer look like? That single habit, kept up consistently, builds number sense faster than almost any other instructional move you can make. And it costs you about 2 minutes of class time. Second, ask the follow-up question. After a student gets a correct answer this week, ask them one number sense question. Does that answer make sense? Is it bigger or smaller than you expected? What would happen if we changed this number? Would the answer increase or decrease? You don't need a special lesson or a new curriculum for this. Just one follow-up question asked consistently that pushes a child from executing to understanding. And third, protect exploration time. If you're in the early grades or you work with teachers who are, here's a direct request. Protect the time before the algorithm shows up. Don't let the pacing pressure rush you from exploration to procedure before the understanding's built. The algorithm gets learned faster and retained longer when the foundation underneath it is solid. And that's not really a philosophical argument. It's just what the research keeps showing. So let me bring this back to that 5th grade classroom that we talked about at the beginning. That student, the one who believed that multiplying always makes something bigger, wasn't failing mathematics. Mathematics had failed them by moving too fast toward the steps before the sense underneath them was built, by treating the procedure as the whole point, when it was only ever supposed to be a tool for something that the student already understood. Number sense isn't a precursor to mathematics. It is the mathematics, the earliest, most foundational, most irreplaceable kind there is. And when we skip it, when we rush past the exploration and the estimation and the sense making just to get to the algorithm faster, we're not saving time. We're borrowing it. The bill comes due right on schedule the moment the mathematics asks a student to actually understand instead of just execute. Build the foundation first, every time, before anything else gets built on top of it. Next time on Show Me the Math Receipts, we're staying in the classroom and we're talking about something that flies underneath the radar in almost every school I've ever visited. The student who finishes first, the one who's done before everyone else had even a small chance to read the problem. What that finishing first is actually telling us about mathematical understanding, mathematical confidence, and the culture that we build without meaning to when we treat speed as a signal of depth. Episode 12 is called First Done is Not First Understood, and it's gonna make you look at the fastest finishers very differently. My name is Asali Smith. This is Show Me the Math Receipts, and until next time, teach boldly, protect student thinking, and always, always keep your math receipts.